Hi, 8th grade. Today, with the electrolysis of water, we're going to do this lab demonstration for this pandemic year. And the objectives of this laboratory activity, as your first copy of your CAMI sheet says, is to decompose water in hydrogen, oxygen gas by electrolysis. I'm going to show you the setup in a second or two. Second, we're going to measure the volume of hydrogen, oxygen gas that we're going to collect at certain time intervals. And then we're going to graph the volume of hydrogen and oxygen gas versus time and determine the average ratio for the two gases. By doing this electrolysis lab, we're also going to determine some physical and chemical properties of hydrogen and oxygen. And then we'll explain how electrolysis decomposes water using the terms anode, cathode, oxidation, and reduction. Okay? So we'll have these objectives met by the time this is all finished, and I'm going to go over and show you the setup for our lab today. This lab does take a little while, so I'm going to kind of piece this video together, and then we're going to come back eventually to our data sheet, and then we'll also come back to our graph. But right now I'm going to take you over to the lab table and show you how the demonstration and I guess how the setup is going to work. Okay? Now, the basics of this electrolysis lab that we're going to do is we're going to have water, and we're going to take, and where our yield sign is, we're going to apply electricity, and we're going to split the water molecule into hydrogen gas and oxygen gas. Now, to do that, we're going to have a setup where most labs they use 6-volt batteries, and they're like lantern batteries, and they're the ones you see in the camping sections of Walmart, and they kind of have that cube shape to them, and there's two springs on top that are kind of spiral. Okay, in years past we've used those. Over the course of time, I've found that these battery eliminators, these boxes that plug into the regular wall outlets, work much better, and they can dial up a consistent DC voltage for as long as I need, as long as there's power coming out of the wall. Okay, so we are going to have this battery eliminator, and it does exactly what it says. It just eliminates the use of a 6-volt battery. And then we're going to have our water, and the water's been treated a little bit with a couple chemicals to make this work a little bit better. First, I've added some sodium sulfate. Remember what the video said when the guy with the goatee was talking about with that video with chemical bonding, how pure water and tap water doesn't have enough electrolytes to carry a charge very, very well. Okay, tapped up water does a better job than distilled water, but you're still looking at it's not going to go as quick as it should. So we add an ionic bond chemical to it, and that's sodium sulfate. Okay, so I put about 10 milliliters of sodium sulfate into that water, and the water I just got out of the tap right here. And then I've also added about 10 drops of this bromethyl blue, which is just a coloring agent to give it a kind of a nice light blue color. Okay, so what you're supposed to do, and this is where it kind of gets tricky as far as the setup goes. I'm going to move this closer to the battery eliminator. We have two little test tubes here, and these two little test tubes are going to fit on top of these. They look like little bolts, but they're electrodes. And one electrode goes to the switches around to the positive red lead, and a positive terminal on the battery eliminator, and the other electrode goes to the black lead, or the negative. Red is always positive, black is always negative. Doesn't matter what you're dealing with. Car batteries, these little electrolysis setups, it's all the same. Okay? And when I turn the power on, voltage is going to come out, electricity is going to come out of the bolt for the positive and the negative. Now, to get this to set up and to stand, first thing we do, we need to make sure all of the air, the atmospheric air, is out of the test tubes. So I'm going to take and I'm going to submerge these test tubes and make sure all the air is out of them. Should be no air bubbles, because any air bubble that we have in there, we know that that air is not pure hydrogen or oxygen gas, which we're trying to get to. Okay? So I'm going to move this a little bit closer. This is where kids have a little bit of a hard time setting this up, because your fingers are just a little too, they're not practiced in doing this, that's all. Okay, so the very first thing we're going to do is take them. Once we fill these up underwater, we stand these up on end. So they're totally filled up. And it takes a little bit of practice. Okay, so there are my two test tubes. They're totally filled with the solution that we're going to use for the electrolysis. And I'm going to put my electrode under the water. And then very carefully, making sure I don't lose any water, I'm going to carefully take the test tube, put it over top of the electrode. I'm going to push down so it stays. I'm going to do the same thing for the black electrode. And we'll try to get this to stand still. Like I said, the setup part is the tricky part for the kids. Okay, and there we go. Now, as it sets up, we're going to be measuring every 3 minutes. I'm going to time myself. Okay, and I'm going to get a little stopwatch. I'm going to time myself, and I'm going to measure the height of the water. Okay, and as the bubbles come off of the electrodes, and I'm going to start this now, and let me get a stopwatch real fast. We'll stop watching my watch. Okay. And every 3 minutes, I'm going to measure the height of the water. And the water is going to go down, and the gas, either the hydrogen and the oxygen, depending on what test tube it is going to replace the water and push the water out. And once both test tubes are totally just about empty, then we're going to come back and I'm going to show you a positive test for hydrogen and oxygen gas. Okay? So I'm going to turn these on, start my timer, ready, set, go. I'm going to go to 9 volts here. You see the bubbles coming up out. The bubbles coming out of this one and this one represent that hydrogen and oxygen gas bubbles are forming, and we're splitting the water that's in the test tubes. See if I can get a close-up of that. Okay, and we have it working right now as we speak. Okay, so every 3 minutes I'm gonna time the, or I'm going to take the height of the water that's left, and as it works, it's going to push itself down and down and down, and eventually we'll get to the end, and then we'll get to, it's going to take a while. This lab usually takes the whole entire period to go through, and then we'll come back and I'm going to show you what it looks like after it's all done, and I'm going to record all my data so you guys can take and use that as we go. Okay? So we'll come back to this in a little bit. We'll just let it work. So it's been about 25 minutes or so. We're about down to the bottom with the hydrogen, almost down to the bottom with the oxygen. We're going to go ahead and try to test a positive test for both of these, for oxygen and hydrogen. Okay? Put you back here. Make sure it's good. I'm going to shut the lights off to make sure that this can be witnessed by everybody. And then I think we're pretty good as far as it. Okay. Now the hydrogen's empty. The oxygen's just almost empty. It took a little longer. There's a reason for that. We'll get into that in a little bit. Okay. Now, we're going to use a splint, which is just a wooden, looks like what you would stir coffee with. And for hydrogen, this is going to make an audible sound. Okay, so there'll be like a mini explosion would happen with the hydrogen. And hydrogen, we know, comes off of the black wire, the negative wire, and a negative lead. Okay, so what we have to do, we don't want any air getting into this. So you almost need two people to do this, but I think that I can do it just by myself like this. So I'm going to get my goggles on. Get this lit real good. I'm going to take my finger. Keeping underwater the whole time. Seal it.
Anyone ordered from Mountain View Cafe? Your food is here.
And then we're going to put this in the presence of hydrogen, and we're going to listen for the sound. And there it was, a little mini explosion. Okay? So that's a positive test for hydrogen. Not very loud, but there's not that much collected into the test tube. Okay? Now for oxygen, let's blow this out. I'm going to take his glowing splint, take the oxygen off the red lead, the red wire, seal my finger around it again, seal my thumb around it, turn this up like this, and as it's glowing, as I stick it in here, I want you to watch and see how it relights. Okay? Okay, so a little bit of relighting happened with the oxygen. It wasn't totally empty. Okay, out of the water, but there was just a little bit of relighting that would happen. Okay, so that's a positive test for hydrogen and a positive test for oxygen. Now to clean this up, we can just pour this down the drain, make sure this is out as far as our flame goes. And then we're going to go back to the data table and look at some of the data we got from the measurements. Okay? Okay, everybody, I'm going to take another shot at the oxygen. Seeing it didn't work out too well the first time. This one, another test tube had been emptied of water and filled with oxygen. We just did the oxygen this time, so I'm going to come around and try to grab it again and show you how it should actually look with the flare up. Okay? I'm gonna light my splint. Gotta be safe with my goggles on. Shut this off. Make sure I reach around. Try to grab this so no air gets in and contaminates it. Seal it up. There's a little bit of water left, that's okay. We're going to take it, let this out. Okay, and that worked pretty good. There's just a little bit of oxygen left in there. So that's a positive test for oxygen. When it flares up like that, when it reignites, just like if you were blowing a campfire, positive oxygen, positive test for oxygen with the glowing splint. Okay, the glowing splint. Sometimes it makes a noise. Most of the time it doesn't. It just flares up. Okay, so hopefully you got a better look at how it's supposed to be. That's a positive test for oxygen collected through our electrolysis setup. Okay? Now, everybody, going back to our data table. Okay, this would be the second page down, your cabinet assignment. What you're looking at, and we kind of obviously knew that the black wire would have been recording the volume of hydrogen, and you'd be collecting hydrogen in the test tube that was attached to the black wire. The oxygen would have been attached to the red wire. Okay? Now, as you watched it, okay, and as I took some videos as I was timing it and measuring it, you saw that one went faster than the other one. Okay? And the reason for that is because that's how water is put together. For every one oxygen bubble I got, I should have gotten 2 hydrogen bubbles. So you're looking at your measurements, the ratio of hydrogen volume to oxygen volume should be 2 to 1, based upon the fact that in every molecule of water, there's a 2 to 1 ratio of hydrogen to oxygen. 2 hydrogens for every 1 oxygen. So the oxygen took almost twice as long to empty out. Okay, and that's just how it always goes. That's how it always will go, based upon the fact that that is how the molecule is constructed. Okay. Now, with that being said, my measurements that you're going to record for this year, for this demonstration, took it all the way to 30 minutes. And at the end of 30 minutes, they were pretty much emptied out. The volume of the test tubes was about 70 millimeters. Okay, so we started out after 3 minutes. We had a volume of hydrogen that we collected in the test tube as 25 and 12 for the oxygen. At 6 minutes, we had 35 collected for the hydrogen and 18 for the oxygen. Like I said, it's not exact, but it's close to a 2 to 1 ratio. Okay? If you take and divide 25 divided by 12, you can come out to a number that is going to give you the ratio between hydrogen and oxygen. Okay, and you guys can divide these for the rest of them. Okay, but it should be 2.08 to 1. That's the ratio of 25 to 12, or the hydrogen versus the oxygen at 3 minutes. Okay? At 9 minutes it was 45 and 23. At 12 minutes it was 55 and 28. 15 minutes halfway was 65 and 33. You can see how it's almost all gone after about 15 minutes in hydrogen. And then at 18 minutes it was 70 and 35. And then it slowly catches up, 70 and 45, 70 and 55. And then at 30 minutes it eventually gets to where they're both empty, or the water is emptied out of them, but they're both full of hydrogen and oxygen gas. This one just took longer based upon the fact that there are twice as many hydrogen gas bubbles forming from the electrode of the black wire than there is from the red wire. Because that's when it splits. There's 2 bubbles on one side, 1 bubble of oxygen on the other side. Okay? Now, down at the bottom, our physical properties we kind of introduced. There was a little bit of a yellow stain in the hydrogen test tube. Okay, and there was a little bit of a blue color in the oxygen. Based on it being in that sodium sulfate solution with the bromethyl blue, those are some of the physical properties that the test tubes and the hydrogen and oxygen gas kind of took over when you were looking at the colors that they made. Okay? Now, the reaction to the flammability test, the burning toothpick, or the splint I called it, and the glowing toothpick, you heard the squeaky pot, the sound that it made, the hydrogen, and then that quick flare-up that the oxygen did. Those would be observations we made to represent the chemical properties. Okay, and the chemical property would be of flammability, how it reacts with fire. Okay, for hydrogen and oxygen. Okay, so these are some of the physical properties we had, some of the chemical properties we had. and that would have been our positive test, because you definitely can't see it, you can't smell it, all those gases are inert. There's hardly any way to tell unless you make them react under a flame. Okay? Now, your job, record these for hydrogen, record these measurements for oxygen, and then do a little division to get your ratios. They should come out roughly to about 2 to 1. When you get down the bottom though, it's going to be less than that because the oxygen is catching up, and that's fine. Okay? But when we first started, 2.08 to 1, as a theoretical, it should be 2 to 1 every single time, 2 hydrogens to 1 oxygen. That's fairly good for an actual experimental value. Okay? Now, the graph we're going to look at is going to take the time in 3-minute intervals, and you're going to graph the Y would be the volume of hydrogen and oxygen gas. Okay, so how it's going to look is right here. Okay, and I'm going to zoom out so you can see this. In your camera, you're going to need 2 different colors. I'll shut the lights off so you can see a little bit better. So down the bottom on your x-axis, you're going to mark in 3-minute intervals all the way out to 30 minutes. On your y-axis, the up and down, you're going to measure the height of the gases you collected in millimeters. Now, the highest you have to go to is 70. So I started counting by 5. So I went 5, 10, 15, 20, 25, 30, all the way up to 70 millimeters, because that's totally full. The test tube is totally full. And what you're going to do is you're going to make a line graph for each one, and you're going to plot the points where they start. The volume of oxygen I used as red, and the volume of hydrogen I used as blue. So in 3 minutes, we know that the volume of the hydrogen was at 25 milliliters, or millimeters. So 5, 10, 15, 20, 25. I'd come over, I'd put a dot. We said that the volume of the oxygen, you're going to use red or whatever color, as long as the 2 colors are different. At 3 minutes was only 12. So 5, 10, and then in between 10 and 15, you're going to put a dot. So just like when we did the heat transfer in that graph with the hot water and the cold water, you're going to have a track of 2 lines, one representing the volume of the oxygen, one representing the volume of the hydrogen on your graph, and they're going to proceed from left to right, and they're going to kind of go up the graph. One's going to go a little bit steeper than the other. Eventually, they come out to a point where they're both at 70, and that graph and those 2 lines should meet. Okay? Make sure there's a title on your graph. Make sure the X and the Y are labeled. Make sure you have a legend to show what color represents the hydrogen, what represents the oxygen. And then every one of these points from 3 out to 30 need to be plotted. And then you connect all those with a line using your CAMI tools. Okay? When you're finished with this, you can hit submit. Make sure the graph is done. Perfect. Make sure your data table is complete. Make sure everything on the data table, underneath the data table with the physical and chemical properties is listed. And this will take care of the lab for today. Okay? So today, with the electrolysis, we broke water into hydrogen and oxygen gas. We tested it. We watched how the ratio of hydrogen and oxygen affected how long it took to collect that gas in the test tubes. And then we graphically represented that sequence from the beginning to end on a line graph. Okay? Electrolysis is a type of decomposition reaction. Tomorrow we'll get into, or later on today rather, we'll get into a couple other different types of chemical reactions. There's 4 altogether. The slime lab was synthesis, the electrolysis water was decomposition, and now we'll cover single displacement and double displacement as your types of reactions. And there's 4 types altogether, so we're halfway. Thank you very much, guys. I appreciate it. Hope you learned something, and let me know if you have any questions.